Okay, guys, welcome to your second day on the PyTorch distributed training for CSCS. First, I wanted to ask if someone has any questions for the yesterday's exercise. And if not, we can start with today's tutorial. And well, yeah, as I said yesterday, we're gonna do today a bit of just-in-time compiler and have a quick look how to benchmark some GPU functions in PyTorch, profile them, and see if you can improve with cheat and so on. And then we're gonna have a look on automatic mix precision that we might use tomorrow. And then I think Rafael is gonna show us a tutorial on some transformer model, a large model training on CSCS. So, okay, JIT, just-in-time compiler, can optimize PyTorch functions, arbitrary PyTorch functions or modules, and it actually generates Torch script off the Python code and can also save and then load later on. And Torch script is actually a subset of Python. It accepts most tensor functions. If you try to using really old PyTorch, you might complain on some stuff, but if you write your own modules, normally that shouldn't be a problem. And it works actually, it's quite similar to Python itself, but there's some stuff that not supported, but it shouldn't be a problem if you're doing general modeling. And it basically creates these computational graphs and, well, it just parses the computational graphs of the PyTorch functions, and then they can be optimized as they are executed, right? That's why it's called just-in-time compiler. So they are not compiled ahead of time. There are two ways of doing that. There is the Torch JIT script. It's just a function that you can give it to you can give in a modular function, and it's going to convert it to Torch script. And again, it's not going to optimize it straight away. But it will be optimized as soon as you start using it, right? So you should always expect some warm up change in performance after the warm up. And it's also a decorator that you can add to your modules or functions, so it's pretty handy. And there's also the JIT trace, which is similar in a way, but it actually expects an example input, and it basically creates this fixed execution path using that example that you give it. And we're gonna see later on a notebook, will make much more sense. But because it has this fixed graph, it can't really handle control flow any sort, like if statements, for example. You're just gonna, if there's any condition in your function, it's just gonna record the graph for the conditions that you used during the tracing. All right, so generally speaking, it's easy to use script and doesn't really make any performance difference. The only difference, major difference, is the trace doesn't really require a warm up because you already parse the graph, right? So it's a bit easier to benchmark, for example, but it has additional restrictions. There's a question from yesterday's exercise. Okay, Mario, we can have a look at this later on. It looks like you didn't convert something to CUDA, right? Okay, so let's go to the practice notebook. If you go to Torch JIT, there's a single notebook. Please update the Git repo. I pushed a lot of stuff yesterday night. So in this notebook, we're gonna, as I said before, we're gonna have a quick look at how to benchmark GPU functions. We're gonna have a very simple example there. How to use the PyTorch profiler, and then JIT compiler, and have a look how is the interplay between Autograd functions and JIT, right? So let's open the notebook. Yeah, please everyone make sure you can open this guy. So in torch git provider. I'm stopping, restart it. Okay, so yeah, addition to the regular imports, I define this OMP number of threads here that's used just for NumPy, but just for the sake of comparison. Let me also open the machine resources here on the side and the GPU resources, which are quite useful when doing this kind of stuff. Whoops. Yeah. Yep. Let's go back there. So yeah, so we generate some small random data set here, just a single matrix to make it simple. And we're gonna have a look on the simplest example possible of, for example, a loss function, right? You're just gonna get the mean square error difference between an input and a target, and which can be simply expressed in Python, right? Just the difference of them and then squared and get the mean of it. As I wrote here, these actually NumPy is not super efficient. You'd want to have these written as an inline code like that. That already makes your NumPy code faster because you can do some smart compilations. But PyTorch doesn't really care about it. It doesn't really try to do anything smart unless you use JIT, and that's the whole point of it. PyTorch in general tends to be very expressive, so it only executes the commands that the user provides exactly in the same way and order, right? So yeah, if I run this on NumPy, we saw it takes about 75 milliseconds, and it's actually using a single core here for whatever reason. It should have been able to parallelize it, but well, anyways. You can parallelize in NumPy for sure if you use a dot product instead. But yeah, if your NumPy is properly compiled with OMP, that should work as well. Convert these guys to torch can be simply done with some from NumPy here. This doesn't actually make any copy of the tensors, right? So it gets the NumPy array that we generated up here and just map them to torch. So this doesn't generate any additional memory allocation. And if you actually change this tx here, you're changing x as well, right? It's really just a reference to the same data. And now I can run the same with Torch, which is really nice on Python, right? With the abstract interpreted functions. So here I have actually no NumPy specific code, and you have exactly the same functionality mapped to PyTorch without any change of the code. And if I change the device to CUDA, I can run the same function again. What I wanted to show as well is if you use PyTorch, you actually should see here a peak using way more processors, right? If you actually use 24 threads, which is the number of CPUs we have, it's not gonna, it is using 100% of the CPU, but it's not going faster. See, it actually got slower because there's a overhead of managing all the threads. So yeah, you always have to play a bit with these parameters instead of just arbitrarily deciding it. But yeah, CUDA, you can do the same, right? If you convert these tensors to CUDA, these, you can see here, there is a copy going on. Sorry. If I just do that, well, the memory is already located, sorry. But these tensors are actually copied to CUDA, right? So it does take some time to do these two operations. But if I do use timeit with a CUDA kernel, it's not gonna work unless you actually call CUDA torch torch CUDA synchronize, which is actually gonna wait for the kernel to finish. So in PyTorch, it does a guarantee that it's actually gonna synchronize the whole code. every time. If you would actually get the item of the result, that would actually work, because item is actually making a CPU copy of the results. So these automatically has to call synchronize, otherwise you can't copy them to CPU, right? But then you benchmarking item as well, right? Which is not really what we want, probably. So instead of that, there is this helper function from Torch, I included up here, sorry. Torch utils benchmark. Yeah, actually, should probably leave this include down there for explicitly purpose. Right, and Torch utils benchmarks has a kind of similar effect as Torch. It's not as convenient, you could say, because you have to use their class interface. This is actually the same interface as Timeit, but the magic from Timeit make it much nicer to use, right? You can just put the number of runs that you want to do and any arbitrary function. You could have something similar here if you would have explicitly globals, for example. If you call that instead, that would also work, right? But in general, it's actually quite nice that you can make sure that the code that you want to measure the time is actually exactly just only has access to these things that you define right here, right? So it only has access to these two tensors that we passed, and only has access to this single function, right? So I'm importing the MSC from main, which is then the one that I just defined, and I'm calling it with the two tensors that we define up here, right? And now that takes actually long, yeah, okay. There's some weirdness when I call it first time, but it should take about less than 1 millisecond to do that on the GPU, right? You see, it doesn't actually use the whole GPU because the tensors are too small still. I didn't want to make something really big because otherwise it would take very much longer, but you can play around with these numbers, make a larger training sample that might give you slightly different results in some things, but you'll serve for the purpose. And now let's have a quick look on the profiler from Torch. And it works nicely with this context that you can define. You define a profiler and tell it which kind of activity you want. If you want CUDA or CPU, you can have both as well. It gets a little bit more verbose. In this case, we're just gonna do the CUDA functions. And this thing, yeah, there's lots of other attributes that you can give, and it give you different outputs. But in this case, I think it actually wouldn't be necessary to have that. But yeah, after we generate the profile, this is gonna run here, and I'm gonna I actually give me a name to this function, so I actually know what I'm running. So you could actually put these in several different pieces of your code with different names, and it then makes it much easier to track it after that. And you can quickly print the results of it by getting the profile that you define here and getting the average of the keys. And this prints a nice table that we see down here. All right. It's slightly hard to see on the notebook, but it's very nice on log files. For the notebooks, you can easily convert just to a pandas dataset, data frame, sorry. And then you can actually see the names a bit better, right? You can see here there are simple MSC function is actually calling 3 CUDA kernels. And you can see the 3 kernels down here. And you see the execution time of them. And these actually sums up to the same number that we saw up here, right? Going back here, you can see that the functions it's doing, it's an addition, which is in the case actually the subtraction, right? And then we have the power tensor for the square, and then finally the mean, right? For each one of these operations, it actually has some overhead in actually transferring all the data to the caches and then cleaning them up and restarting the kernels and so on. So generally, when you write CUDA code, you wanna make sure that you make as less kernels as possible, right? Ideally, this should be a single function, but the reduction is really hard to put in the same function. So normally, often you're gonna have like the kind of map reduce paradigm, right? So you do like all the parallelizable stuff together, and then you reduce at the end. And this is what you do when you're programming OMP as well, and so on. But yeah, as we said before, Torch doesn't try to do anything smart, so it just actually called the three functions, right? If you look at MSC again, he actually has three functions, right? You have the subtraction, square, and then the mean. So it's actually gonna call three kernels. Another thing here is the Chrome trace, which is kind of interesting too. You can actually see the ordering. That's very similar to the Nvidia profiler that you can also run on the CLI functions. So you can run your whole script on the Nvidia profiler, or you can make these little pieces and export them to these JSONs. You can see that I already opened, is that the right one? That's the MC trace, yep. And then, yeah, don't worry too much about the CPU stuff. You can see here the CPU and then the GPU. The CPU is often offset because the times don't really match. But at the beginning and the end, you see it took like twice as long. This also has the influence of the profiler itself. So you're more interested in the CUDA stuff, and these actually takes the 900, almost 1 millisecond here exactly. And here you can see really the three operations, right? Scrap the addition, and then this is the power, the square. There is a tiny little one here, which is, I think it's memory set. Here's that, yeah. Just setting 4 bytes. So I guess this is properly allocating the output of MSE, and then for the mean, sorry, and then the mean kernel. So you have a reduce operation, right? And they kind of always take about the same. Like the mean should be much faster to be calculated, right? Because you don't have to copy the tensors and so on. But yeah, anyways, we'll see later what we can do about that. So now let's have a look what we can do with that with JIT, right? Here there's a link for the documentation, and we say again there's the 2 ways of doing it, using script and trace. And so using script can be very simple. You can just wrap whatever module or function they're using, and then you get a scripted function out of it, right? And then from this function, you can call code, and it actually gets this Torch script code representation of it, which is basically, it's basically Python, right? You see it has annotated types, it assumes everything is tensors. If you don't annotate itself, but then it translates those Python operations into the storage functions. But this is also Python code, right? You can actually execute this as Python. It would work fine too, right? And you could do just that. Yeah, this is totally fine as well. Sorry, obviously it doesn't know the namespace. But yep. So it's really a subset of Python. And he also has this graph representation that it's used later on to do the optimizations. But here you can see it's basically the same, but translated into their A10 library, which is their C++/CUDA library. And each one of the Python functions get translated into a A10 function, basically, right? And say this is not optimized yet, right? This is just the raw code. And we're just gonna, the script's only gonna be optimized when we actually run it. But we're gonna see this in a second. The second way of doing that is using trace, as we were saying before, right? And you can do the same thing. We can get the function and put it through trace, but you actually need to give example inputs. And there's a restriction here that the inputs can only be tensors. JIT actually accept other types. They just have to be annotated, as we said before. We're going to see that. But trace only accepts tensors. But when you do trace, as we're going to see when we benchmark this thing, it's not going to require a warm-up. So it's already went through the code for that specific input. You can see when you get the graph, he already has the sizes of the tensors inside the graph, and which could be interesting for debugging. I don't know if he actually sees it. You can see on the code. No, you can't see on the code, obviously. Yeah, but on the graph, you see the sizes and their internal representation. Right, and there is also the decorator for JIT. Right, it works exactly like the function itself, right? It's basically declaring this function and then parsing it through the script. As I said before, if you have anything that's not a tensor, you have to explicitly annotate it. Otherwise, it's gonna assume it's a tensor, which might be okay for you or not. But it's, yeah, well, it's nice to annotate everything anyways. So you could just annotate like we were doing on the example before, you know, torch tensor. Right, this is a good practice anyways on Python. And yeah. And yeah, this also returns a tensor. That's true. Oops. Right. Yeah, if you're writing Python functions, it's nice to have the annotations anyways. So yeah, why not? If you're doing JIT, you have to do them basically if they're not tensors. But yeah, you see, you can actually have conditions on the code, and it handles that without any problem. And it still can optimize your code, but it's only gonna do that in real time. So now, if you run that through the benchmark, we're gonna get some weird timings. So let's see the 3 benchmarks that I put here. I got the traced, the script, and the GTMSC, which is the one from the decorator, right? Okay, and same inputs on all of them, and I run them 100 times each, all of them. And you can see that the traced one is much faster, right? But the other ones take much longer. But this is just because of the warm-up time that I was talking before. If I run this code again, you can see that now they all take about the same time, right? Makes no difference which method you use, but you need to run it at least once, and you have to wait for the CUDA synchronize, obviously, and after that, you're running optimized code. And now, if you compare the time that we have now with the time before, how much we had before? We had 978, 973. And now we almost have half of it, right? 600. It's, yeah, 1/3 was reduced, basically. And using the profile, we're going to be able to see that. So you can see that the code is the same. So we can't really see the optimization in the code, unfortunately. But if you run the profile, you actually can see that now, instead of having 3 kernels, I have a single one. And it creates this fused subtraction and power kernel, which takes about the same time as the simple subtraction, right? Which makes sense because most of the kernel is actually just loading all the caches and the data into the cache. So the stream processors can actually go through it. because you actually have a single operation per element, right? And that's basically it. So GT is very simple, right? And can be very powerful for sure. There are some quirky things depending on the order that you put the operations. You might optimize in slightly different ways. So you should always play a bit around and profile and see what happens, right? This also generates trace. So let's have a look on the trace. Right, now we have this large fuse kernel, and this is the reduction, right? Yep, and that's it. And yeah, it's interesting that he managed to launch both fused functions from a single kernel as well. So that saves the overhead for the CPU as well. So yeah, you see there's really just one kernel being launched, right? But yeah, there's in PyTorch, there is also this function MSE that you're probably familiar with, which does exactly what we're doing, right? It does exactly the MSE loss that we just done here. And we're gonna compare the result here, and you can see that it's actually really close. We can actually print them, so you can see. It's basically the same. Item normally gives you slightly better output. Right. Even, yeah, because it's using exactly the same kernels. It's going to give you exactly the same result, even to a high precision. But yeah, if we benchmark the functional MSE loss, so I'm importing MSE loss from function. I guess the color is not very good for the screen. Am I running on presentation mode? Oh, that should be be better now. Sorry for that. Yeah, if I'm running the function MSE loss, it actually takes a bit longer than the GTID one. And it doesn't make much sense because this guy is a single CUDA kernel, right? So let's see what we can see about it. If you profile it again the same way, yeah, again, the table is a bit hard to read here, especially in presentation mode now. But you can see that it's actually launching two kernels. But they're basically the same. Here's the MSE kernel, which does exactly like the fuse subtraction and square, and takes about the same time. Let's go back here. It takes a bit longer, actually, but well, very similar. And the reduced kernel, right? Just as before, takes about the same time. Let's do this again. Yeah, it's pretty consistent, actually. Took even less now. Okay, so their implementation is not as efficient as it could be, I guess. But you see the GT is slightly faster, but it's doing about the same operations. But there is one difference, that the reduced operation is actually running on a separate kernel, because this reduction here is conditional. There you can, I think there is an additional parameter for MSE loss. I should have opening here. Sorry, I lost myself. Let's have a quick look on the documentation. See, he actually has a few parameters. Yeah, it has this reduction thing. If we look at the code of it, here we go. That's our MSE loss, right? And part of all the boilerplate stuff. Sorry, unfortunately, can't see. Yeah, we'll have to have a look on the C++ code. But yeah, the reduction is conditional. It doesn't necessarily need to do the reduction every time. You could opt to skip the reduction completely and just get the tensors, the different tensors. And that makes a difference because now we we don't know if we need to launch the second kernel or not, as JIT could actually solve that by having two different paths, two different graphs for the two different paths, right? With the reduction, without reduction. Generally, just gonna use one of them on your application. So that's how JIT makes sense, right? But yeah, okay. This is so good. But let's have a look on what really matters. Like when you're doing deep learning training, the backward pass is generally what takes longer. That's the real bottleneck of the whole thing. As a rule of thumb, it's say that backward normally takes 3 times as long as the forward pass. And that's pretty much, yeah, that's very close to reality from what I've seen. Mainly because not only you have to calculate the gradient function, which is very similar to the forward by itself, but you also have to keep all the gradients and then propagate them, right? So there's a lot more work to be done, obviously. So we can try now to get the use backward to use Autograd on the JIT function that we created, right? So this is gonna call the Autograd with the recorded operations from JIT, right? So you can see we import the same functions here and just do the backward. But as we said before, this requires a warm-up. Otherwise, you're gonna have some weird times here. So always you're gonna need to call the function at least once and wait for synchronize, or you could run the benchmark twice. That would work too, right? And to be able to do backward, I need something that requires gradient. So I just clone the X, the CUDA X, and say that it requires grads now. So this is basically a parameter now, a parameter tensor. And when I call backward, this is gonna try to find the gradients for var, right? And let's see the times. So now the JIT MSC backward take quite a bit longer than the MSC loss, all right? And basically because the MSC, the function MSC implements its own backward function from scratch, and it doesn't need to use Autograd, right? But the JIT has to use the Autograd function. And generally, yeah, it's better to optimize your Autograd function separately. As we were able to see here quickly, I tried to implement a simple MSC Autograd function. Take a second to go through this code. There's more comments than code, but yeah. We're gonna see here, oh, 1 second. I'm implementing the forward pass, which is exactly what we had before, right? Just creating another function just to make it clear. And I would JIT that function, right? And I create the backward pass then, which is just the gradient of MSC. The ordering here is a bit weird, but the gradient of the MSC is basically, well, the gradient of mean is basically 1/n, right, times the gradient of the rest, and the gradient of that is 2 times the difference. So here I have the gradient of the power and the gradient of mean. And the backward functions always take the upstream gradient, right? So you go layer by layer during the forward pass until you calculate your loss. And when you do backward, you go back from the loss and all the layers one by one, but they carry the gradients from the one before. And by the chain rule, you just multiply them one by the other, right? So you just multiply by the output here at the end, and you're done. And the Autograd function is the only thing in PyTorch that I find a bit ugly that's not very Pythonic. Let's say we have to define this class with the static methods forward and backward. And these get called, this is very C++ like style of coding, right? And actually on the C++ library, it's exactly the same. So no, it makes sense, I guess, to have the same interface. But yeah, the Autograd functions, there's no mystery really. The only extra functionality it has is this save for backward. So you have to save the input of every layer in order to use them during the backward, right? But you save the input and then you calculate the MSE, and then during the backward, you gather the inputs that you saved before, and this is all handled by the Autograd function, right? And then you pass that to the backward function that you put. Again, carrying the gradients from upstream, right? And you have to use apply from that Autograd function. So I'm just renaming, well, overwriting the JIT MSC that we created before with this new Autograd function. And here, just doing some basic testing. If you do want to define a function like that, you probably need a lot more testing, but for the sake of it, we're just going to check if this matches with the MSC loss from functional, right? And again, I'm going to do that little trick with var in the backward, and I'm just keeping the gradients that it generated from this backward here as fg, the function gradient. And then I'm doing the same backward with our new function, right? And I'm gonna, I have to wait for the synchronize. And then I'm comparing these two. So the gradient, the var grade is the one that I would just generate with the JIT MSC, and the fg is the one from the function MSC. And this is, true, right? You see. So seems to be fine. Yeah, it would be nice to have more tests. Like Hypothesis is a good library for unit testing this kind of stuff, because you can have random inputs and run them as many times as you want, all different types and so on. And then now I want to benchmark both of them, right? Same benchmark that we did before. I already warmed up it here, so I don't need to do it again. So I'm going to benchmark JIT MSC backward against MSC loss backward. And now we can see that the times are very close, right? There is very little loss here. As if you compare with before, let me just pop this for a second. Ooh. Yep, so before I had 2 milliseconds, and now we're down to 1.8. So we got 10% improvement, basically. And we can have a quick look in the profile of that again. Now I added here the CPU as well, just so we get better annotation, but you see it gets really noisy. It has lots of functions going on. You can reduce that by using just the CUDA functions. And now you can see very nicely here that I have the subtraction and the power as we had before for the forward pass. But now I also have the subtraction multiplication, right, from the backward pass, which is exactly this operation, right? So you can, this becomes a single number, and then this becomes a single kernel. You can't do much about the upstream gradient, unfortunately. And you can see that another major another major thing that's taking time is the kernel that we're gonna see now. This guy is actually what's adding the values to the gradient, right? So we can't do much anything about that. But you can see there are 4 kernels, and we can have a quick look on the tracing. Here we go. This one that I saved had the CPU annotation, so you can see all the stuff, what's going on the CPU, and then how it gets translated to the GPU. So I have the forward pass here, right? And our mean reduction, and then it gets to the backward pass. And so this is multiplying the upstream gradient, right? That you can't, unfortunately, JIT doesn't work very well yet with the Autograd function. So it should, in theory, be able to fuse these two operations. And that would take exactly the same time as it's already taken, so we could actually completely eliminate this operation. But yeah, for whatever reason, the Autograd function can't work with cheat in that way. And this here is actually adding then the calculating gradients. Sorry, to the actually var gradient. And there's also nothing we can do about that, right? But you can see really nicely what each function gets mapped to. There's always an offset from CPU to GPU, which makes it a bit weird looking here. Then you can see the synchronize just waiting for the GPU later on, right? Okay. Yeah. So yeah, there's a disclaimer here, right? This is just the loss function, obviously, and it's the simplest loss function for sure. And as we said before, the model is really always dominated, the compute of the model is dominated by the backward pass, right? And this is the often just matrix multiplications, and they can't be cheated. Well, they can, but you wouldn't be using the cuDNN kernels, which are very efficient. But yeah, what I wanted to say is actually, yeah, spending time optimizing a loss function might not make much sense, because actually you're spending most time on the backward pass. So if you want to spend any time optimizing anything, is going to be optimizing the backward pass, right? So you should, instead of profile a single function, you should profile a whole model or parts of it, and then see where you can actually improve and what you can do about it. Yeah, but yeah, I think this gives a tiny demonstration here on how you can use grading functions. This kind of function is not just for loss functions, right? To be clear, you can do anything like that. Every function on PyTorch can be defined like that. And the C++ kernels and the CUDA kernels are defined in a very similar way, and you can also define them with cheat. To make a fair comparison, we try to run this thing without cheat, and you see what is gonna happen. So it still matches, and now it takes a lot longer, right? See how many kernels. So we launching 8 kernels, 8 different kernels. So there is an overhead every time you launch them, and yeah, they also. It's interesting the addition is taking that long, but okay. Yeah, so just by reducing the number of kernels is generally where you can save a lot on these small functions, right? So let me go back, just. If for your use case, Torch script and JIT compiler is not enough, there are also other alternatives, right? You can write your own C++ extension. I put a link to a nice tutorial here. And the function looks very much like the Autograd function that you look above. You just have to write the kernels in C++. But the A10 library is very useful too. You actually sometimes have a very Python-like interface. So it's not too bad to switch between the two. And there is also a newish OpenAI Triton, which, yeah, I put a link. Well, maybe we should open it quickly. I put the link to the softmax direct. Okay, but yeah, if you go on tutorials here, there are a few different ones, and the softmax, I think it's the easiest to see what's happening. So you have a comparing against the JIT function here. Just they're doing softmax and an activation function, I think, right? That's the graph. No, sorry, it's just the softmax. But you can see the comparison between Triton and JIT for really large tensors. at least their use case here has a massive difference. But this is for extremely large tensors, right? So Triton allows you to define block sizes, and the code is up here. Yep. So it allows you to define block sizes just in the way that you do in CUDA, but all in Python. Yep, you can see here how you grab the block sizes, and then you can split the tensors and coordinate the work basically around the multiprocessors, right? But yeah, it's a very interesting topic for sure. We could discuss further that if you have any interest. But yeah, I think that's it for JIT. If there are any questions, I'm happy to take them. Otherwise, I guess we could take a 10-minute break, right? Okay. We see you guys at 10. I'll stop sharing here. All right. Coming back. Then now let's have a quick look on automatic mixed precision training. So yeah, everything we've been doing so far is being in single precision. That's the default float type for PyTorch. I think in science, people use a lot of double precision or even more than that. But in neural networks, that it's not really required. Actually, we talk about adding noise over the layers and so on. So generally, if you want to find algorithms that work under noisy conditions. Anyway, so yeah. The slightly difference of precision between double and single precision, it's not a big deal. And most of the tensors and the scalar values are often as well also very close to 0, between 1 and -1 or around that range. Yeah, probably a bit higher if you have a standard deviation of 1, right? But not extremely bad. So the half precision would actually be okay for most of the cases. And in theory, yeah, we would need half of the transistors for the computation, obviously, and also half of the memory to store all these, for example, the intermediate values, the parameters, and so on. Right, but there is definitely a precision loss, so you have to be aware of that. And what happens to automatic precision? What does it mean for us at Piz Daint here with our P100 GPUs? We will see that the pointwise operations are about 50% faster. However, when you use actually large matrix multiplications, often we're going to use cuDNN for that, and they have very efficient kernels. But for P100, they generally operate at float point 32. So we can't really have any performance gains there. But we do get memory savings. We do only need 50% of the memory to save the activations, for example, right, during the training. So in general deep learning, using automatic mixed precision allows you doubling your batch size pretty much. And when you do that, it can actually be a bit faster as well, because you can, with a larger batch size, often you can better parallelize your pipeline. All right, but as we're saying, there is the problem of loss of precision. When you're too close to 0, the values can actually be truncated to 0 itself, and for example, and that can be very problematic, obviously. I didn't put the source here, but this image is from, I think, the original paper, the first one I've seen at least for mixed precision. And this is on a LSTM, recurrent neural network. And if you know, like, it's already quite fiddly to train them, because they have these very long loops of backpropagation through time. And loss of precision there can be can get you to very weird results. But they show here that scaling the loss already solves that issue, right? So the green line is their solution, which basically just multiplying their loss by 128, and that's enough. So yeah, there are ways, but ways to work around that. But as we're saying, yeah, the range here, I put the range of the float point 16 is only between 65,000 positive and negative. So if you go any higher than that, it's gonna go to infinity as well. So you have to make sure that your, for example, your inputs and everything else is within the range, right? But this is actually a different problem normally. It's actually going the other way around. It's actually getting closer to zero, right? And so yeah, basically, we can use float point 16. But there are a few quirks, and yeah, people come out with basically these two solutions for the same problem with loss of precision, right? Which is first autocasting. So when needed, you're gonna autocast between float point 16 to 32 or back to 32 if it's necessary, right? And what we call gradient scaling or loss scaling. You have to keep your loss away from zero. And this is done basically by just multiplying your loss by a large-ish scalar. And in some cases, that can be done dynamically. So you can probe your backward pass, and if you see any numbers going to zero or infinity, or not a number, sorry, not zero, you can actually increase your or decrease your loss scaling, right, to accommodate for that. In native PyTorch, I think since version 1.7 that it supports automatic mixed precision natively, it's defined basically the outcasts with a list of a table of functions, and those functions get automatically autocasted to float 16 or back to 32 if it's in 16 already, right? And you can see the most matrix multiplications up here, convolutions, which are just matrix multiplications, and some very simple activation functions can be done safely in float 16 without much loss of precision. But functions that are very nonlinear or get very close to zero or have any division on it, like the MSE loss we saw, logs, anything that will have logs, or powers, and the norm has division as well, will be automatically cast back to 32 if using half precision, right? And that's how it's basically solved. And in the native PyTorch, you can easily adapt your training loop by adding the gradient scalar. So you create a scalar, and then when you're doing the forward pass, you wrap your forward pass around with this autocast context. And so within these contexts, it's gonna automatically cast those functions that we saw before, either to float point 16 or 32 when needed. Casting has a cost, obviously, but if the operation is fasting FP16, then it can be worth it, right? And then the scalar works in the same way. Basically, you wrap the loss function, the result of the loss function on the scalar, and then you're gonna call backward from the scalar, right? And this is gonna scale the loss by the dynamic scalar that he has installed here. And during this step, instead of doing optimizer step, we're actually gonna do the scalar step. And this is actually gonna check if there is any problem within the optimizer step. It's gonna basically just skip that step and roll back, basically, and don't increase the scalar, for example, right? So you're just gonna keep trying to increase this scalar every time, but if there is any problem, it just goes back and stays on the same one. And and the update can then automatically find if it should go up or down. That's basically. So you have to add those 5 lines basically on your train loop, and you're done pretty much. We're gonna see in the hands-on notebook later on as well. So the first actual implementation of AMP for PyTorch was from this library called Apex from Nvidia. And it's not only about mixed precision, right? This library holds several optimizer, like fused layers, fused optimizers, like fused Adam, fused Lamb, and has some support for distributed training as well, and lots of helper tools. And NVIDIA is constantly adding more stuff to it. For example, it has fuse batch norm recently and fuse layer norm. We could actually speed up your training, so it's worth checking it out. So it basically has the CUDA kernels for some parts of the model that could be optimized, right? But on the automatic mixed precision with Apex, they had this optimization level, which can go from 0 to 03. If you're familiar with C++, that's pretty much like GCC. All right. So 0 basically means no optimization at all. And then 01, it will cast some ops to float point 16. Not batch norm, for example. So it's basically similar to what Torch Native is doing. It keeps all the weights, gradients and the optimizer momentums in float 32, but the activations are stored in float 16. So all the intermediate activations from the forward pass, they're going to be used for the backward pass later on, are stored in half precision, and that saves half of your memory in many cases. Obviously, it's not going to save any memory that's used by the model itself, but in CNNs, generally the models are not very large, so this allows you to have double batch size already. O2 has additional optimizations, so now the model weights will be cast to float 16. Not the batch norm again. But the optimizer momentums are gonna be kept at single precision, and it also keeps a copy of all the weights before it went cast, and it keeps synchronizing the weights from float 16 to 32. All right. So in float 16, we got the weights and the gradient as well, because now the operations are actually between float 16 and float 16, right? The inputs and the activations are in float 16, and the weights are also in float 16. So you don't actually need to cast the operations anymore. Yeah, apart from the batch norm, as usual, right? And there's also O3, which is basically float 16 everywhere. And actually, no, actually, I think it's wrong. Yeah, it doesn't have loss scaling by default. But in Nvidia Apex allows you to change each one of these different parameters, each one of these different optimizations one by one if you wish. So you can make your own subset optimizations if you want. And it's basically done by that. You just wrap your model and optimizer with this AMP initialize, right? And after that, you do your forward pass normally. And then during the forward pass, the model wrapper will automatically cast the things and so on, if it's needed, right? And then during the backward, it's similar to the torch one. You have to wrap your loss with the scalar. But it's a static scalar in this case. And then you call backward on this scaled loss, right? And that's it. So yeah, it's very simple to use it, pretty much. And here you can change the optimizer level. You can also, there's also a link for the additional options where you can actually go to each one of these optimizations one by one if you want. You can change the batch norm back to 32 if you want, or yeah, or use the master copy or don't, or and so on. The dynamic scaling or fixed scaling. So if you already know where your loss goes to, it's faster to have a fixed scalar, right? You don't have to skip the steps where you went wrong, basically. Now we're gonna have a look on the notebook, and we're basically gonna have a look comparing, like, again, MSC, some very basic instructions, how they work in float 32 against float 16, sorry, and then how we actually we benchmark both of the two libraries, the two implementations of AMP, all right, quickly. Okay, so please open the other notebook. Again, it's so on AMP, and automatic means precision, right? So the imports have nothing, just apart from the Apex here. And NumPy has a nice table from the types. So you can see here the resolution from float 32 against float 16 already. And this is the main problem in deep learning, right? So if it gets smaller than these, it's gonna go to 0, basically. And there's obviously also the max issue. So if you overscale your loss, it's also gonna go to infinity. And that's how we actually do the dynamic scaling, right? If it gets to infinity, you stop scaling, and that's it. For completeness, there is also the bfloat 16 that Google Brain created for their own hardware, right? With TPUs, you can use bfloat 16, and the new GPUs from Nvidia are coming out with that as well. And there's even some ARMs that support bfloat 16 nowadays. So in the future, we're probably going to be using bfloat 16 for a lot of things, at least. So you can see the max is as high as the float 32, right? Almost. The only issue is the resolution that's very, very slow. Basically, you're operating here in the log scale the whole time, right? So you only care about the magnitude of your gradients. If you only care about the magnitude of your results, that's fine to use float, bfloat 16. But it's not gonna work with P100, so we're gonna skip that for now. And here, if you look at the torch half tensor, right, I put all the limits here, and so you can actually see how this implicates on reward. So you see it has some loss of precision when you have, well, always anyways, but if you have a small value, you can see that it has basically the same problem as is quoted with the resolution, right? It cannot express anything below the fourth decimal of any number or any magnitude, basically. If you get really close to the max, or the smallest possible values are e to the -8. If you get close to that, the precision gets really low, and that's what you're trying to avoid with the loss scaling as well, right? And if you go any lower than that, it just goes to 0, right? And also, if you're very close to the limit, it gets just down to the limit itself, so you can see really easily. And if you go over that, it just goes to infinity, right? So these are actually the last numbers that you can actually have on with the float 16, right? But if your problem is within these bounds, then it's fine. If you can survive with some noise, as we normally do in neural networks, it seems to be fine during the training. It doesn't, in many problems, it does not change your accuracy, right? So now let's run some little benchmarks. I'm gonna go to the simple MSC loss again, just because it's easy to use, but we're gonna make now 2 tensors, one in single precision and one in half precision. See here, float 32, float 16, right? I call them CX and HX, and they're slightly larger than we had before. But we're gonna use the same loss for sake of simplicity. right? And I don't know if you actually run this, but sorry, let's run everything. Yeah. So you can actually see the MSC is almost twice as fast in float 16 compared to float 32, right? So for this kind of operation, it's much faster to use float point 16. But as we're going to see later, yeah, matrix multiplications normally don't work very well. And that's the main limitation. It'd be interesting to try to actually create a either C++ kernel or a Triton kernel and try to see if it gets any better than the float 32 batch matrix multiplication for half precision. But anyways, so now, yeah, if you profile that, you can see, obviously we have the 3 kernels, but you can see the types that you get to half here, and you can see the time space just get halved in both of the cases. So yeah, if you're doing anything like that, it's definitely convenient, but obviously there is a cost, right? So if you subtract the full precision, the single precision to half precision, there is a difference. And this is close to the resolution that we saw before as well, right? We can profile the memory of that. I create this little helper here, which basically allows us to create a context where it cleans the memory cache to the cache in the beginning and at the end again. And then it calculates the difference in the max memory allocated from the beginning to the end, right? Very simple, but it works, yeah. And now if I run the backward pass with single precision against half precision, you see that it uses literally half of that, right? This is storing the activations from the before the MSC during the backward pass. So that's exactly half of it, obviously. This is the size of that, basically. But yeah, and this is the main use of half precision for our GPU, at least, is to reduce the memory footprint. So if your model is largish and you want to reduce, you want to increase the batch size, but you can't because you run out of memory, you can use half precision and you can double your batch size. And let's see, like now on a more realistic example. I'm using Torch Visual Models here. I got DenseNet 201, which is reasonably large. Not massive, but enough for us to see the results. And if you try to if you feed batch size 64, I'm gonna generate some random data with the batch size, 3 channels, and the image size. It could already. And the targets as well, so we can actually run some loss and some backward pass on it, right? And just as a helper function that I'm gonna repeat just to make sure that everything is initialized cleanly. And our baseline is the regular training loop. So I'm gonna calculate the memory usage on doing the whole step, right? So I'm gonna create the model, the optimizer, and then for each step, I'm gonna do the forward pass, calculate, subtract the log loss, log softmax, sorry, do the cross entropy against the target that we defined before. So regular cross entropy with the negative log likelihood loss, and code backward, optimize the step, and zero grad, right? Just that like we did before. Then I'll add the torch synchronize here, obviously, because otherwise we can't really benchmark it. And that makes it easier. Now we can actually use the time it magic. So it's a bit less verbose. And at the end, I'm gonna delete the model and the optimizer. I think my helper does call garbage collection. Yeah, so The clean is gonna go call the garbage collector and clean the cache. So the model and the optimizer are properly cleaned, and then it reports the GPU usage, right? So on the float 32 baseline with batch size 64, this uses 12.5 gigabytes of RAM, right? So it fills most of the GPU. So if I do this again, it'll be fine. Yeah, it's totally fine. We're gonna see the memory goes all the way up and then it gets cleaned up again. And right, and this takes about half a second per step. And now we can compare against the automatic mix precision, right? So remember the native PyTorch use AutoCast and Gradyscaler. I put the list here and the links to their implementations if you want to have a proper look. But yeah, basically, remember, we just need to define scalar, right? And then wrap the forward pass onto the AutoCast context. And then the loss backward, excuse me, we're gonna use the scalar for the loss, which will multiply your loss by the scalar. We use the save step with the scalar, and then we update the loss scaling, right? And that's it. So the rest is the same. And if you run this as well, you can see now we use much less memory, right? It's half of the memory, but it actually takes slightly longer instead, right? This is a bit unfortunate, obviously, but you could run the profiler. I didn't put it here, but you're gonna see that it uses these pre-made kernels for matrix multiplication, and it's not using what, at least the half precision version of them are not as efficient as the 32. And there's also the autocasting going on, which has some costs as well. All right. Now let's have a look on the Nvidia Apex implementation, which is almost less work to be done, right? You get the model and the data and the optimizer. Then I have to wrap the optimizer and the model on the AMP initialize and do the regular forward pass during the training step. But then the loss I have to wrap around the scale loss and call the backward in scale loss, right? And the optimizer is already wrapped, so this step here is actually the AMP step. So yeah, it's a bit clear. Well, yeah, it's more transparent, I guess. But and if you run that again, AMP has this weird variables thing that it does every time you call initialize, but it shows you which optimization that you chose. There's a little summary of it, and then it has the each one of the optimizations separately, right? So the AMP is enable. Yeah, I'm using OChooser. So the model is cast to float 16. So we don't need to patch the functions because everything's float 16. The input is cast to 16 as well, right? But the batch norms are kept at 32, and there's a copy of the master weights, and the loss scale is dynamic. So every time you call the loss scale backward, it's going to actually calculate see if you can increase the loss scale, and sometimes the optimizer step can fail, but it's just going to skip that step, and then do it again until it finds an optimal scale. And and that takes about the same time as the native though. And it uses also half of the memory, right? So we're using 6.4 gig instead of the 12. So basically the two are very similar. We can do it with O1, for the sake of it. Feel free to experiment with other parameters. So in O1, you can see that the model is not casts, but it's patching the functions like the native open implementation does, because it's only patching the functions, not patching the batch norm. So you don't need to change the batch norm. There is no master weights copy. Lost scale is also dynamic. In 03, I think by default, everything is in float 16, even the batch norm, and it's not using log scale by dynamic log scale. So you can easily add additional options here. I think they have exactly the same name, hopefully. So this is actually faster because the batch norm in float 32 from cuDNN is faster than the float 16 implementation from Apex. So it is like slightly faster, but it's still not very different from the native one. So we recommend using the native because there's less dependency as well. But as I said, in Apex, there are actually lots of interesting optimized layers and optimizers that let's definitely have a look at. We're not going to add any here, just not to complicate things. 01 is generally okay. I left 02 just to be different from the native, right? Okay, yeah, I have 2 little exercises for you. Sorry, I'm losing my voice. With this lockdown, I'm not used to talk anymore. So the first one, yeah, you can see that we're using way less memory. So in theory, you can easily increase the batch size here, right? And you can see what is the largest you can get. And yeah, that's a very interesting thing here. If I double the batch size, I basically has the same memory usage from the half batch size at float point 32, right? But because I'm using a much larger batch size, it should have taken, if I'm going back here, sorry, if I run this float 32 step twice in order to consume 128 images, this will take me over a second, right? Everyone agree with that? But if I do the same 128 images at half precision, that takes less than a second. So how much is the gain? It's about 5% gain, I guess. Oh, it's actually more. Yeah. So you can speed up a little bit your training by having a larger batch size. And in some cases, is way more useful to run a training in larger batch size, right? If you're doing your own modeling, you probably know about that. So certain problems require a certain batch size. In ImageNet, often people report the top accuracy at 1,000 or 2,000 batch size. And we obviously wouldn't be able to fit that in our GPU, right? I won't try to increase here to 128 because this is going to go over and it's going to break. But you can play around, especially with Apex AMP. You can fiddle with the options, the special options, and see if you can get a larger batch size than that. If you do run out of memory, you probably need to restart your kernel. I'm sorry. Sometimes you cannot recover from it. But please report the max batch size that you find. And if you've done the last exercise with the distributed ImageNet training with DALI, now you can go back to it and add the AMP support to your training loop, right? You can pick one of them. I would recommend use the native AMP. It seems to be slightly faster, I think. Yeah, not much of a difference, but at least you have less dependencies. Although Apex has some interesting DDP-like wrapper as well themselves, where the weights, if you're using O2, the gradients are actually in float 16, right? So there is actually only half of the data that you have to transfer between the nodes. That's definitely useful. We're gonna see, I think Rafael prepared some tutorials in deep speed, and deep speed is also gonna use something very similar to the Apex. I'm not sure if it's actually using Apex itself, but it's probably gonna use something like O2, where there is a master weights copy and so on. All right, so I'll leave you guys with that. Please let us know what is the max batch size you found. And I guess we could have another break, or Rafael, do you wanna start?
No, yeah, let's do a break.
Okay. Another 10 minutes, 10:45.
Yeah, sounds good.
Okay, see you guys then.
Good morning. Now we can continue with the next example. So please, if you could pull again from the repository, we have pushed this directory BERT squad, and we're going to be using it right now. So if you can push and go to the directory in the notebook. In this example now, we are going to be doing the task of fine-tuning the BERT model. The BERT model is a transformer model from Google. And then we're going to so it is already, we're going to fetch it, pre-train it from the Hugging Face database of transformers, and we're going to tune it in a data set that is called SQUAD. That means Stanford Question and Answer data set. We're going to fine tune it to for the task of giving a paragraph. Sorry, we're not giving a paragraph and a question about this paragraph, and the question has to be inside of the paragraph. So the paragraph itself has to answer the question, and we're going to fine tune this model. So when we leave these two pairs, it will return the position where the answer starts and where it finishes. Okay, like for instance, if we were to give this paragraph with the questions, which model are we going to fine tune, then the model would give us this character. So the answer that starts here, and this character. So and the answer finishes here, or BERT. Okay. So the first thing, if you all are ready with the you already fetched the notebooks. Okay, there is no question. If you already fetched the notebooks, we can start in the notebook 0. And this is just try to understand, to go over the data and see how the data set is composed, and how the training data is so the training set is prepared. Okay, so we import some stuff, and so the first thing is, so okay, let me Okay, the first thing we start with the raw data. So the raw data, we're going to fetch it from these URLs. So this is yeah, some bash thing that we put inside of the notebook. I already run it, but if you run it, we can run it again actually. You will get something like this, and your data is going to be in the folder where you are right now, in a directory called cache, and then within it data. So now if you want to get rid of this thing, you can click here, or if you want, you can just mark all this and comment it, and so like that you avoid to running it by mistake another moment. So okay, so we got the data. Now the data is here, cache data, and it's these two JSON files, and so we can open it. So open it is nothing special. We use plain JSON from Python. We load it, and we see what this. We start with the. We're going to see the train data because the evaluation of the test data has the same shape. So we just look at one of them. So if we see what is inside, it has something, a key called data and a key called version. So version is it's going to be this 1.1, the version of the data set. So we're interested in this part here. So if we print the length, we order, so we loaded 442 of these paragraphs, and for training and 48 for testing. And so if we look here inside of data, we take one of these 42, of the 442, I took 91 because it talks about the Alps, so, but there's nothing special about it. So it has the title, it's called Alps. Then it also, besides title, it has paragraphs, and it has 87 different paragraphs in this topic of the Alps, okay? And each of these paragraphs has different context than this are going to be the different paragraphs, okay? So they are called contexts, and so they are also paragraphs, and together with them, each has a set of questions and answers. For instance, this context here, this paragraph, has what country the Alps are located in, and then it has the answer, and the answer starts in the character 190, and the text, the reply, well, it's not a very good answer, but it says that it's Europe, so it will end in the character 190 plus 6, okay, and so on. So every of these contexts has many questions, and then okay, this is the raw data. It is yeah, it is like that. So here for this kind of task, the first thing that we have to do is tokenize these sentences, and tokenizing the sentences means to separate it in words, or in sometimes I don't know, in some cases, if a word is not there, it can separate in small chunks, so it's called subwords. But the main idea is to separate it in different pieces, like it can be words or commas, parts of words. Okay, so and for that we are going to use these tokenizers that are from Hugging Face, from the Hugging Face library, and so we are going to use this bear tokenizer, and you can do it with this one, but I did this notebook from based on some post from this post here from Keras and TensorFlow, and they use a combination of these two, and I will explain you later why. And so there are two tokenizers, and but the idea is that we download this tokenizer, the bear tokenizer, and from it will save in the hard drive. It will save this vocab txt, which is a list of all the vocabulary that can be like it will be used to separate this in pieces. So based on the vocabulary, this thing is going to go to different pieces of words or parts of words. Okay, and at the end we're going to end up using only this tokenizer. Okay. So we create a tokenizer. So this is a bit long, but in summary, it's a function that's going to give us this separation of the sentence. And so we can pass the tokenizer over the data set. So here, this is a bit, I put this hidden in this utility dataset utils. But the idea is that that it is going to go through all these examples and answers, and it's going to check that all the answers are inside, all the answers are given here are in fact inside of the paragraphs, and we have set here also a max length, which is the maximum number of tokens that we're going to have in a that we want to have in a paragraph. For instance, if the paragraph is too long, we are going to stop it in 394 words, and well, no words, tokens. And this utility is also going to check that we don't include in our training set these numbers, these answers that are outside of where we of where we truncated the paragraphs. Okay, so it takes a bit of time, but it's not that much. It's only 1 minute, and for the training set that is smaller, it's about maybe like 10 or 15 seconds. And okay, so we created this train squad examples, and from it we created these two things that we're going to use for training. So let's see what we did. So the first thing is this thing is a NumPy array, and the shape is the number of pairs, paragraphs, and questions. Remember that for one paragraph or context, for one of these paragraphs, there are many questions. Okay, so okay, so there are 86,000 training samples. Okay, we get one of let's say one of these samples. I just chose this one. I don't know why. And we see that this is of a type. So it's a NumPy array of type squad examples. So, and in a squad example, they just create it because with it they can filter and see yeah, what I mentioned before, if the answers are inside of the piece of text that we save from when we truncated the paragraphs. Okay, so we have this, and now let's have a look to X train and Y train. So this is the training set. So X train has 3 things inside, and all are of the same shapes. So 86,000 by 384. And if we look, so let's start with the first one. If we look here, we see all these numbers here and a lot of zeros at the end. So this thing is because besides here, besides tokenizing the sentences, the paragraphs, sorry, this function also encoded these words into numbers so they can be passed to a model, because the words cannot be passed to a model. So in this case, so we have here, so this 1996, yeah, probably, so I guess, unless it was coded differently, it should be something like it's not the same paragraph, but an Alps is going to correspond to another number, and French and a mountain, etc. So we have numbers for every word, and these zeros is they are just padding, so all of them have the same size, So when we do batches, a batch can be passed to the model. So okay. So this is the first component of Xtrain. So the next, here we can see, so if we decode back, we see that actually, yeah, that's why I took this 2029, which is the Alps. So it's the Alps, okay? And here we are just decoding, no? And okay, the next X1, Xtrain 1, sorry, is called attention mask. So the attention mask is using this model to create batches for. So when you create, sorry, when you create these batches, I said that it needs to be padded. You have to do zeros. We have to tell the model where to look at, and we have to tell the model, okay, this part, don't look at it. We are only interested in this. So all this thing is padding. Don't pay attention to that. And this is what the Xtrain 1, sorry, 2, the last component has. Okay. So if we put here, we have ones. So until this point here, and this is going to be ones for everything that is a number, that is a word, it's a token, and 0 for everything else that is padding. Okay. So if we evaluate our Xtrain 0, the sample of the Alps, in every word where the attention mask is 1, what we get is the numbers, so the tokens, and then when we decode, we see only the Alps. Okay. And yeah, well, actually, this is not very illustrative, because always the code doesn't show just takes out the padding. But if you see here, we don't have any padding. Okay. So the last one, so the train X1 component is called token type IDs, and this one is only to specify what is a paragraph, what is context, and what is question. For instance, remember here when we look at the mask, the ones arrive here, so the paragraph ends here. So the paragraph and the question ends here, and here it ends here. So they have ones. So there are all these zeros. That all these zeros are say that is type 1, which for us is the context, and all these ones is the type 2, which are the questions. Okay. And same thing if we evaluate where Xtrain is 1 is 0, we get the paragraphs, and if we evaluate where Xtrain 1 is 1, we get the questions. Okay. So this is the part related to the context and the questions, and the other part, the Y's, are just the positions. So we have one position where the word starts for every pair of question and paragraph, and where the same for where the word ends. So here we can print at the end the context. Yeah, looks like this with the question, the answers, and the training sample would look like this. Everything, of course, encoded. So paragraphs plus question at the end, and the y is where it starts and when the answer starts and when the answer finishes, and together with that the attention and mask to say which part of this thing is padded, and the type IDs that to say which part of this is question and which part of this is answer. Okay, so if there are questions, could you please check your microphone? It seems that it is hitting some support. Oh, I'm sorry. Yeah, I think I was moving myself. Yeah, I'm sorry. If I make a noise again with the microphone, please let me know through just unmute yourself and let me know. Don't let me wait until I drive you crazy with the noise. Okay. Okay, that's it. So for the data set, we can have a look to the training. The training is way easier than dealing with the data. We're going to see. So we go now to the notebook 1, and yeah. So here is going to be very similar. The beginning. So all this part, this is the tokenizer. And this is the model. So the model we get it is going to be BERT for question and answering. That you get it from here, from transformers, which is the Hugging Face library. I put some links here to it. And so we have the model. So I print something here because this model was already trained, and we are loading some weights on it that may not correspond to the totality of the model, because there are some parts that are frozen only for the fine tuning. So in the fine tuning that we are going to get a model this already pre-trained and adapted to a specific task. There are some parts of the model that are frozen, and this is I think what this is complaining about, but this is fine for our case. Okay, so this is expected if you're initializing big question answering from the checkpoint of a model training another task with another architecture. Okay, so this is fine. And so we load our data set, and yeah, we process it. Remember, this is around a minute. And while this is working here, I want to show you the result of the model. So at the end, after we train, we should get something like this. We have a question and model answer and the reference. And you see this is only after one epoch. The question, all the reference and the model's answers are really on spot, are very close. And you see, so here we print around 50, I think. Yeah, we print 50. Yeah, we print 50 examples. Okay, so now we are going to evaluate, and we're going to see first that at this point before the fine tuning, all these questions are going to be wrong. Okay, so this is okay. So we have the data sets. So here for training, we create this PyTorch data set using the dataset API. And here what we do is to this X and Y. So X, remember, has the paragraph with the question, the attention mask, and the type IDs. Okay, so we pass it here. So these are the first three things. So first is here is the paragraph and the question. Here are the type IDs, I think, and these ones are the attention masks. And here is where the answer starts, and here is where the answer finishes. So we put everything in a tuple of tensors, of PyTorch tensors, and that's it. And we said here that the length of the data set is the length of X, so the 86, yeah, this 86,000. Okay, and now we set a batch size 16. That this is the maximum I found that can be fit in one GPU here in Piz Daint. And yeah, we create the data loader, we put the batch size and shuffle through. I run this one, yeah. Sorry, do you have still noises from my microphone?
Sometimes, but generally it's fine.
Okay, I will try to. Let's see. Maybe yeah, if I keep it like this far from my. Okay, sorry about that. Okay, continue. So we pass the model to the device here, and we set it for train. This setting it for train. Yeah, it said something in the model that yeah, like batch normalizations and this kind of stuff, I think, and for training, and then you would have for evaluation model eval that it will freeze some parts of the model that that are not used for training. Okay, but it's not really important. And okay, so we have the model now in the device, as it says, for training. In the particular case of BERT, I'm not sure exactly what it changes, but anyway. So okay, we create an optimizer and we use this learning rate. This learning rate, I got it from this Keras tutorial, but it's already well tuned. If you go a bit larger than this one, you may get you may get it can be very large and you may get wrong results at the end. Well, if you don't do anything to adapt it to the training, if you keep it constant, this is a good value. Okay, and here we do the training. So the training is I put only one epoch because in one GPU it takes some time. And so we iterate about the over the training loader. This is the typical PyTorch things that you know. Zero make the gradient zero the gradient, sorry, and get the outputs from the model. And the model we pass the things that we talk about in the previous notebook. So we have the input IDs. This is the text itself, the text and the question. Okay, tokenized, of course. They call it input IDs on Hugging Face. Token type IDs, you know, is two zeros for the questions and one zero for the paragraph and ones for the question. Attention mask is to separate what is padding and what is text or question. Start positions and end position. Okay, and all of them we pass it here to device. And in the output, the output zero of the model, this is going to give us the loss. So it's set like that on the Hugging Face class. So we don't have to create a loss ourselves. You see, we only created the optimizer. So we get the loss, and the loss we apply backwards, and and we do the optimizer step. So if we at this point we haven't run anything, let's have a look, evaluate the model, and see which answer it gives us. Let me see if I have. So we put the model as eval now. Now it's not training. Look here. Before it was training, and now we put it as evaluation. And I will copy here to do not lose the questions now. So this one I can comment. Well, no. this one I can comment. So and so let's evaluate model CPU model. No. Yeah, I think. Sorry. So here I will just save the model as we have it, because in this part of the notebook, since we are almost using the whole GPU for training, I just save the model to file and load it again on the CPU, and then do the training, the testing on the CPU, because otherwise we won't have memory left after we run the notebook. And then here is complaining that the model that I'm using, I put it on the device. But anyway, so we can have this model CPU. I think this is what we have. Yeah. And here we go back to model CPU. Okay. So this is the model that we just save it without doing any training, just to see which kind of answers it gives. Now you see, sometimes it doesn't give answers, so that means that it gives a number that is completely outside of the text. Okay, and in this case it gives something, but it should be Thomas. Okay, this is a reference. So maybe Thomas B. Etzel, and it gives conservative. You see, so at this point the model is not good for this task. We want to end up with something like this. Okay. So here I think I have to. I put the model. No, okay. Set to train. Okay. So we go back and we can do the training. So the training takes it takes some time, and so it is 11:16. So my idea for this, I will stop here. And yeah, maybe because I really went fast over this, maybe explain you the rest. So this is a training, and so I will explain you this quickly, and I tell you afterwards what to do. So here we have the model we train on the GPU, and yeah, we want to save it on disk and load it. And load it again on the CPU. So we do the evaluation on the CPU, because we don't have more memory on the GPU for evaluation at this point. So we use storage save, and then yeah, model state disk, and we put where we want to save it. And here is just to use a hash that depends on the time, so I don't overwrite other models that I have saved. And then here we create the model the same. This is exactly the same thing that is at the beginning, and we say model CPU, and we load it from the one we saved, and we have to pass map location torch device CPU. And if you want to load it in the GPU, I put here commented way. And so this is model CPU that I think in yours is a model, so this is not right. And at the end here I hid also another utility, a vals utility, that it checks like things for this, like this one, for instance. It doesn't give an error if the numbers doesn't exist inside, are out of range, and it does other formatting and stuff to give you this table. Okay. But the idea is that you select some samples from the data set, from the evaluation, sorry, from the test set. And so you pass it here, and you have to pass this one that has these squad example types, not the the ready data because to deal with this kind of stuff. And that's it. This is what we'll print you the table already formatted and everything. And okay, so going back here, my idea for this, since it is already 11:20, is that you take this example and make it distributed using the things that you learned yesterday. And yeah, so here in the two, we have an example. You can do it in the notebook if you want, using IPC Magic. And here we have a reference. If you use 4 nodes, or no, let's try to use. If you use 2 nodes, it should take to train around 20 minutes, maybe a bit less. And you have this one for reference, and that's it. So just encourage you to play with it and try to go to the notebooks, understand better what we discussed, and yeah, and see the outputs. The only difference that compared to this one, no, sorry, compared to this one, that you may need to change when doing the distributed version, besides the obvious data parallel and things stuff, is when saving, the model is wrapped by data parallel by the data parallel API, so you remember. And to save it and being able to load it on a single node on the CPU or even in the GPU, it needs to be saved instead of like this, that we do model state dict. We have to do module state dict. Otherwise, you will have to. It will be loadable only in the same number of nodes that it was loaded before. Okay, that it was trained. So that's the difference, and the rest is the same. And yeah, for that, since for the CPU you want to do evaluation only in 1 node, you can use this minus target 0. So you will be using only one CPU. Sorry, one node. And yeah, if there are questions, let's discuss now. Otherwise, yeah, I would leave you and we can stop the call. And today in the afternoon, this is just time for you to practice everything that we have seen so far. And yeah, the reservation is going to be valid until until 5 p.m. So you have all the afternoon to play with this kind of stuff. So if you want to train with 64 nodes or something big, I would ask you to use your own Piz Daint account, because this one is shared. So this one, try to keep it in 2 nodes or something like that. Okay. And yeah, everything, the data, all this kind of stuff, they are loaded automatically. And if there are questions or anything, we are going to be in the chat. Just let us know, even in the afternoon at any time. Okay. So other questions now?
Yeah, if I may ask, where will the recordings be available?
The recordings, yeah, they won't be available right now. They will be available maybe in a couple of weeks because they will be edited, I think. But normally they go to the page of CSCS, cscs.ch, and then you look there for tutorials.
Okay, thank you.
Okay. Okay, so nothing in the chat. Okay, then we can stop here the recording, and again we're going to be available for discussion in the chat, or yeah. See you tomorrow then. Bye, and thank you. Yeah, thank you for coming.
Thank you.